Welcome to Differential Equations, Section 2.3, Linear Equations. Objective number 1. Define a linear differential equation. A linear differential equation is a type of differential equation in which the dependent variable, often denoted as y, and its derivatives appear in a linear fashion, meaning they are not multiplied together, raised to any powers, or included in any nonlinear functions like sine of y or e to the power y. A first-order differential equation of the form f of x dy over dx plus g of x times y equals h of x is called a linear equation in the variable y because both y and dy over dx appear only in the first degree and are not multiplied by each other or raised to a power. To make this equation easier to work with, we can divide both sides by f of x, assuming f of x doesn't equal 0, to obtain dy over dx plus g of x over f of x times y equals h of x over f of x. So let's introduce some simplified notations. So let's define p of x as the g of x over f of x, which is the coefficient of y after dividing by f of x. And then we'll define q of x as h of x over f of x, which is the term on the right side of the equation. So now our equation takes the standard form dy over dx plus p of x times y equals q of x. This form is useful because it allows us to apply a technique called the integrating factor method to the equation. For a first-order linear equation of the form, we define the integrating factor as I of x, which is equal to e to the power of the integral p of x d of x. The integrating factor, I of x, is chosen specifically because it allows us to rewrite the left side of the equation as the derivative of a single term, I of x times y. And this transformation is useful because it simplifies the process of finding y. So let's see what happens when we multiply both sides of the differential equation by the integrating factor, I of x. So we'll take our standard form, and we'll now multiply each term by I of x. So we have I of x times dy over dx plus I of x times p of x times y, which equals I of x times q of x. Okay. So notice that the left side of the equation is the result of the product rule for the differentiation. The product rule for differentiation states that for two functions u of x and v of x, we have the derivative of u of x times v of x over d of x equals u of x times the derivative of v over the derivative of x plus v of x times the derivative of u over derivative of x. In our case, u of x equals I of x and v of x equals y. So by the product rule, the derivative of I of x times y over d of x equals I of x times dy over dx plus y times the derivative of I of x over dx. Since we know the integrating factor, note that the derivative of I of x with respect to x is I of x times p of x by the chain rule. So the derivative of I of x times y over d of x is going to equal I of x times dy over dx plus y times I of x times p of x. This allows us to rewrite the left side of the equation as the derivative of a product. So we can simplify that left side to just I of x times q of x. So from there, we can then solve for the equation for y by integrating both sides with respect to x. So when we take the integral of both sides, we then have I of x times y equals the integral I of x times q of x dx plus c. And then solving for y, we just divide both sides by I of x, giving us the following equation: y equals 1 over I of x times the integral of I of x times q of x dx plus c. So this is the general solution to the first order linear differential equation. Objective 2, solve linear differential equations. Okay, so here we are given the following problems, and with these problems we're asked to find the general solution of the given differential equation, give the largest interval over which the general solution is defined, and then determine whether there are any transient terms in the general solution. And transient terms just refer to the temporary part of a solution that decays over time and doesn't persist in the long term. Okay? But before we go into those, let's go over our step process. Let's review what exactly we're going to do in order to solve linear differential equations by getting y by itself. So the first thing we'll do is rewrite the equation in standard form. So that's going to be your dy over dx plus p of x times y equals q of x. Next, we'll find the integrating factor, I of x. Then we'll multiply everything in the differential equation by I of x. Then we'll integrate both sides with respect to x, and then we'll solve for y to obtain the general solution. All right? Okay, let's solve some problems. Okay, our first problem. Find the general solution of the given differential equation. Give the largest interval over which the general solution is defined, and then determine whether there are any transient terms in the general solution. And our first equation here is y prime plus 3x squared y equals x squared. Okay. Notice that this equation is written in the standard form for linear equations. So what we can do now is identify the p of x and q of x from our standard form. So we have y prime plus 3x squared y equals x squared. So our p of x will equal 3 of x. Our q of x will equal x squared. Okay, that's our first step. Rewrite the equation in standard form, and from there we were able to identify our p of x and q of x parts. Step 2, find the integrating factor. So that's going to be I of x, and I of x equals e to the power of the integral p of x times, well, actually p of x d of x, there's no times. Okay, so when we substitute in p of x into this, we get e to the integral 3x squared dx. When we simplify this, we'll get e to the x cubed. Okay, so that's step 2, finding the integrating factor. Step 3, we're now going to multiply everything in the differential equation by I of x. So e x cubed times y prime plus e x cubed times 3x squared y equals e x cubed x squared. Okay. All right. Next, we are going to simplify the left side. All right. Notice that this is the answer to the product rule of e to the power x cubed y. So we will take the derivative of ex cubed. Oop, my pen here is a little. Ex cubed y over dx equals ex cubed x squared. Okay. Now we can integrate both sides with respect to x. So we'll take the integral of d e x cubed y over dx equals, I forgot to write my d of x with respect to x. And we take the integral of x squared, let's rewrite that, or rearrange that, e to the x cubed d of x. Okay, now we can simplify. So the left side, we'll just have e to the power x cubed y equals the integral of x squared e to the x cubed d of x. So to simplify the right-hand side, we're going to have to use u substitution. So let's get some more space here. So let's let u equal x cubed, which means du equals 3x squared dx. So to substitute for dx, we will have to divide both sides by 3x squared. Okay. So when we substitute that into the right side of our equation, we'll have e to the x cubed y equals the integral of x squared e times e to the power u times 1 over 3x squared du. All right. Then when we simplify this, we will get the x squares cancel. So we'll be integrating 1/3 times the integral of eu du, which equals 1/3 eu plus c. Okay. Now we know that u equals x cubed, so e x cubed y equals 1/3 e to the power x cubed plus c. Okay. So now our last step is to solve for y to obtain the general solution. So that means we'll be dividing everything by e to the power x cubed. So we'll have y equals 1/3. When we divide this first term by e to the power x cubed, the e to the power x cubes cancel, giving us plus c. E, when it's in the denominator, we can move it to the numerator, minus x cubed. Okay, and so this is our general solution. Okay, so our directions also told us we needed to give the largest interval over which the general solution is defined. Okay, so the solution is valid for a x that exists between -infinity and infinity. So the transient transient, yep, that's spelled correctly, transient term is c times e to the power negative x cubed because it decays to 0 as x approaches infinity. Okay. Alrighty, that's our first problem. Okay, next we have y prime plus 2 over x y equals x minus 1. Okay, so we know that our equation is written in standard form. So we can identify our p of x, which is 2 over x, and our q of x, which is equal to x minus 1. Okay. So next we need to identify our integrating factor, I of x. So that's going to equal e to the power integral of 2 over x d of x. So when we simplify this, we'll get e to the power 2 natural log of the absolute value of x, which will just equal x squared. Okay. So now that we have our integrating factor, we can multiply each term in our differential equation by our integrating factor. So we'll have x squared y prime equals not equals, we're still at plus x squared times 2 over xy equals x squared times x minus 1. Okay, simplifying, we get x squared y prime plus 2xy equals x cubed minus x squared. Okay, so we know that the left side here is the derivative of x squared y over dx, which equals x cubed minus x squared. Okay, so now we're going to integrate both sides respect to x. So in doing so, we'll get d of x squared y over dx equals the integral of x cubed minus x squared dx. The left side will equal x squared y, and then the left side we will integrate. So we'll get 1/4 x to the 4th minus 1/3 x to the 3rd plus c. Solving for y means we're dividing each term by x squared, and so we'll get y equals x squared over 4 minus x over 3 plus c over x squared. So this would be the general solution, or we can say the explicit solution for our differential equation. So the solution is valid for x greater than 0 or x less than 0, but not at x equals 0. because the term 2 over x is undefined the transient term is c over x squared because it decays to 0 as x approaches infinity. Okay. So since x squared is in the denominator, we know the denominator cannot equal 0 or it would be undefined. So all our x's, we can use any value of x as long as x is greater than 0 or less than 0, but it can't equal 0. And then we know our transient term is going to be c over x squared because it decays as x increases. All right, our denominator gets bigger and bigger, then our value gets smaller and smaller. Awesome. Let's do the next one. All right, we still have the same instructions for this third problem. All right, but our dE, we have x times dy over dx plus 3x plus 1 times y equals e to the power negative 3x. All right, so as you can see here, our differential equation is not written in standard form. So the first thing that we're going to do is write our problem in standard form. So we have x times dy over dx plus 3x plus 1 times y equals e to the negative 3x. So our first term here must only be the first derivative of y. So we need to then divide every term by x. So we'll have dy dx in our first term plus 3x plus 1 over x y equals e to the power negative 3x over x. And so now our equation is written in standard form. So we can identify our p of x, which is 3x plus 1 over x, and our q of x, which is e to the power negative 3x over x. Okay, so that is step 1. Now we can do step 2. So let's find our integrating factor, I of x, which will be from the formula e to the power p of x d of x. So we'll have e to the integral p of x, which is 3 of x plus 1 over x d of x. Okay, and we can simplify our power. We can split our ratio into 2. So we'll have 3 plus 1 over x d of x, which when we integrate, we'll get e to the power 3x times x. Okay, or we can write it as x e to the power 3x. Either way works. All right, now that we have our integrating factor, we now can multiply everything in our differential equation by our integrating factor. So x e to the power 3x times dy dx plus 3x plus 1 over x times x e to the power 3x equals, oh, I forgot a y. I forgot a y. I forgot my y. Let's just add it here at the end. Equals e to, that's the power 3x times e to the negative 3x over x. And then we can simplify. So first term can't simplify anything yet. Second term, our x's cancel out. So we're left with 3x plus 1 times e to the 3x y equals, the x's cancel here, and then these two terms cancel as well, leaving us with just 1. Okay, we know this is the answer to our product rule. So we are going to rewrite that as the derivative of x e to the 3x y over dx equals 1. So we'll then take the integral of both sides. So I forgot my dx. Do you forget your dx sometimes? Or am I the only one? It's okay though, we caught it. All right, then we can simplify our integral. So we will have x e to the 3x y equals x plus c. Then we want to get y by itself, so we will have y equals x plus c over x e to the 3x. And that will be our general solution. Okay? So the solution is valid for x greater than 0, the transient term is c over x e to the power 3x, because it decays to 0 as x approaches infinity. Okay. All right. So e doesn't exist in the negative, so we can only have positive x values. And we know one, x can't be negative, one because of e, and then the other because our denominator can't equal 0 as well. So x must be greater than 0. All right. Okay, great. All right, our next exercise. We're asked to solve the given initial value problem. Give the largest interval over which the solution is defined. So this is very similar to the problems that we've just done, except for the fact that we're now dealing with an initial value problem, meaning that we're given an initial condition. So we are going to follow the same steps that we have been working with, except for now when we get to the general solution, because we have an initial condition, we can find the particular solution for this DE. Okay, so let's solve it. So we have our dE, x, y prime plus y equals e to the x, right? We are going to rewrite this in standard form by dividing all terms by x. So our first term is just the first derivative of y. So we have y prime plus y over x equals e to the x over x. So now we can identify our p of x, which is 1 over x, our q of x, which is e to the x over x. This then allows us to find our integrating factor, which is e to the integral of 1 over x dx, which equals e to the power the natural log of x, which then leaves us with the absolute value of x. So now that we know our integrating factor, we're going to multiply each term in our dE by our integrating factor. So we have the absolute value of x times y prime plus the absolute value of x times y over x equals the absolute value of x times e to the power x over x. Simplifying, we get the absolute value of x y prime plus y equals e to the power x. We then can rewrite the left side as it's the answer to the product rule of e of the absolute value of x, y over dx, and that equals e to the x. We then will integrate both sides. Okay. When we integrate both sides, we'll get the absolute value of x, y equals e to the power x plus c. Okay. So now we can solve for y. So we have the absolute value of x, y equals e to the power x plus c. So in solving for y, we're dividing everything by the absolute value of x. So e to the x plus c over the absolute value of x. Okay, so this right here is our general solution. So now that we are given an initial condition, we're going to apply it to our solution. So we know y of 1 equals 2. So this is our initial condition. Let me label it for you. Okay, so substituting this into our general solution, we have 2 equals e to the power 1 plus c over the absolute value of 1. So this simplifies to e plus c. So then c equals 2 minus e. So now that we know what c equals, we can rewrite our general solution as y equals e to the x plus 2 minus e over x. And this is our particular solution. Okay. All right. So the last thing that our directions told us to do was to give the largest interval over which the solution is defined. So since the integrating factor the absolute value of x is undefined at x equals 0, the largest interval is 0 to infinity. Okay, awesome. Okay, alrighty. Next, we have x squared plus 1 times dy over dx plus 3x times y minus 1 equals 0, with an initial condition y of 2 equals 2. Right. So, given that our dE is not written in standard form, we need to write it in standard form. So, to do that, we are going to divide everything, right, by x squared plus 1. So dy dx plus 3x over x squared plus 1 times y minus 1 equals 0. So p of x equals 3x over x squared plus 1, and q of x equals 0. So our integrating factor will be e to the integral 3x over x squared plus 1 dx. We're going to let u equal x squared plus 1. So du equals 2x dx. Okay. So in substituting for dx, we will get 1 over 2x du. Okay. So when we rewrite our integrating factor, power, so we're focusing specifically on the power right now. When we rewrite this power, we will get 3x over u times 1 over 2x du, because I substituted in for dx. So simplifying, we have 3 over 2 times the integral of 1 over u du. So this will equal 3 over 2 natural log of the absolute value of u. So this equals 3 over 2 natural log of x squared plus 1. Okay. And we don't need the absolute value because no matter what x value we substitute for x, it will always be positive. Okay. So knowing the power, we can now give our integrating factor e to the power 3 over 2 natural log x squared plus 1. When simplified, gets us x squared plus 1 to the power 3/2. Okay, so that is finding our integrating factor step. So now that we found it, we multiply each term in our dE by this integrating factor. So we have x squared plus 1 to the power 3/2 dy dx plus x squared plus 1 to the power 3/2 times 3x over x squared plus 1 times y minus 1 equals 0. Okay, so we know the left side is the derivative of x squared. Actually, let's put a bracket here because I'll be multiplying. X squared plus 1 to the power 3/2 times y minus 1, and that equals 0. Okay, so next we can take the derivative of both sides because we're trying to find y. So we'll take the derivative, not the derivative, we'll integrate both sides. Oh man, it's a lot of derivatives in integrating, but we love it. So x squared plus 1, 3/2. So I'm just going to rewrite this real quickly, just so you have it in your notes. 0. Oh, I forgot my dx again. Pop it in there. There we go. Okay. When I simplify, I will get x squared plus 1, 3/2 as a power, y minus 1 equals c. Okay, so I want to get y by itself, so let's divide both sides by the x squared plus 1 term, which will get me y minus 1 equals c over x squared plus 1 to the power 3/2. Then I will add 1 to both sides. So I'll get c, well, y equals c over x squared plus 1 to the power 3/2 plus 1. So that is my general solution. But now, since I'm given an initial condition of y of 2 equals 2, I can substitute this initial condition into my general solution to find c. So 2 equals c over 2 squared plus 1 to the power 3/2 plus 1. Okay. So that will equal c over 4 plus 1 to the power 3/2 plus 1. So that will be c over 5 to the 3/2 plus 1. And all of this equals 2. And so we now want to get c by itself. Okay, so let's subtract 1 from both sides. So let me rewrite this here on the screen for us. So we had 2 equals c over 5 to the power 3/2 plus 1. So we'll subtract 1 from both sides. So that gets us 1 equals c over 5 to the 3/2. So then c will equal 5 to the 3/2, which we simplify to the square root of 125, which equals 5 square root 5. Okay, so substituting that into our general solution, we have y equals 5 square root 5 over x squared plus 1 to the power 3/2 plus 1. And this now is our particular solution. So the solution is valid for all x that exists between negative infinity and infinity. There's no restrictions in the denominator for the domain. Yay, we did it. All right, next. Okay, our last exercise. Again, we're given an initial value problem, and we're asked to give the largest interval over which the solution is defined. This is a trig-based differential equation, but the process is still the same. So let's do it. All right, so we have y prime minus sine of x times y equals 2 sine of x. Okay, so we can see here that this is written in the standard form for linear differential equations. And we have an initial condition of y of pi over 2 equals 1. So let's begin. So I'm going to just rewrite my dE here. So I can then identify my p of x, which is negative sine x, and my q of x, which is 2 sine x. Then I can find my integrating factor, which will be e to the power integrate negative sine x dx. When simplified, will get me e to the power cosine x. Okay, so now I can multiply each term in my dE by this integrating factor. So I will have e to the cosine x times y prime minus e to the cosine x times sine x times y equals e to the cosine x times 2 sine x. Okay. The left side here is the answer to the product rule of e to the cosine x times y. And that equals cosine x times 2 sine x, sine of x. Okay, so next we will integrate both sides. So I'll just rewrite our integration equation. Okay, then we are going to have to use u substitution. So we'll let u equal cosine of x. So d of u, not d of u, du equals negative sine x du. Okay, so that means it's not du, that should be a dx. dx. So we know then that dx will equal 1 over, so be negative sine of x du, which we can then substitute into our integration. So let's do that. So on the left-hand side, let me rewrite our integration here for us so that you can see how it's connected. Cosine xy dx equals integral of e cosine x times 2 sine x dx. So when I insert my u substitution, the left side will simplify to cosine x y. Then we'll have 2 sine x times EU times -1 over sine x du. So, in simplifying, we will then have -2 EU plus c. The signs cancel. And then e cosine of x, y on the left-hand side. Okay? All right, now we can substitute our cosine back for u. So e to the cosine x plus c. Okay? And then solve for y. So y equals -2, because we'll be dividing everything by e to the cosine x, so that cancels, plus c e to the negative cosine x. So I moved it from the denominator to the numerator, making the exponent negative. So this is the general solution. So now I can apply my initial condition of y pi over 2 equals 1. Okay? So when I do that, I'm going to substitute that into my general solution. So I get 1 equals -2 plus c e to the negative cosine of pi over 2. So that will be 1 equals -2 plus c times e to the power 0. E to the power 0 equals 1. So that would be -2 plus c equals 1. So then c equals 3. Since c equals 3, our particular solution is y equals -2 plus 3 times e to the power negative cosine x. Okay. All right, so we need to then state where this solution is valid. So the solution is valid for all x that exists between -infinity and infinity. Alrighty, great. That concludes the end of section 2.3. Enjoy.